to join will join later. So let me just begin by clarification. So for those who seem to be sure as to what I was asking in the first question, let me just find. Okay, I'll try and write there. So in the second assignment, I gave you a formula. So, but the question was, what about the Hamiltonian? So the Hamiltonian is the standard one for the hydrogen atom. So just okay. I was. I think I just logged out. But my point was that in the first question of the assignment, what I want was that I am getting asked as to what exactly I want you to do, given that I didn't give you the Hamiltonian. So if you look at that question, so I'll go through quickly as to summarize what I wanted you to do. So I gave you this very complicated formula, which you can get by solving the Dirac equation and plus j half plus square root j plus a half. So the question is, what exactly do I was I asking? So if you look at this formula, there are squares, there are square roots, and then there is square root to the minus 1/2. My question was that I want you to start expanding everything out. So for example, you can try to expand things inside that square root, where you get that square root of j plus half minus alpha squared. You know that alpha will be smaller than 1, so you can take out the j plus a half, and then you will be left with 1 minus alpha squared over j plus half. And then you just make use of the binomial approximation, 1 plus x to the n is approximately equals to 1 plus nx. So this is just an example of the things sitting in the denominator. So that will give you j plus a half of 1 minus half alpha squared over j plus a half. So you expand the square roots, you expand the 1 over 1 plus x, then you expand the 1 plus pi to the minus half. And doing all these expansions, in the end, you should check that you are able to reproduce what we did for the fine structure constant. So if you remember, if you take into account the fine structure of hydrogen plus also the spin orbit coupling, we were able to get the expression 15.6 over n squared 1 plus alpha squared over n squared of n j plus a half minus 3 over 4. So once you've expanded that, you should try to reproduce this result. So I think the first question doesn't really require much physics. You just make use of the binomial approximation, that this was approximately equals to 1 plus nx, and then you expand everything, you expand the square roots, expand everything. So then let's start with this lecture. So let me just summarize, because I think the last lecture was slightly too technical, but one of you or some of you seem to be getting this stuff because they were asking me about pointing out typos and stuff like that. Let me just summarize what we did in the lecture, the previous lecture. So we switched to the Dirac interaction picture, and in the Dirac interaction picture, we were able to write down the equation for the evolution operator in the interaction picture. So this was T Ti over dt. This, we found that this was given by Vi of U I T Ti. Right. This was the equation that I think maybe we spent maybe 30 minutes trying to get. It's just that I had to initially tell you about the Schrödinger picture, tell you about the Heisenberg picture, and then move on to the interaction picture. But once we had this equation, then we solved the equation for the evolution operator in the interaction picture. So this gave you UTI, this gave you 1 minus I over h bar integral dt prime of Vi ui, and this was some sort of an integral equation. So the way that we solved this was that we said that because the interaction perturbation is very small, initially we could ignore that part. So this means that we could just approximate that to 1 in the interaction picture was 1. Then we took this ui, then we plugged it back into this equation star. This gave us u1 of in the evolution operator in the interaction picture. We found that this was going to be given by 1 minus I over h bar integral Vi of t prime dt prime going from ti to t, right? And then we took this again and then we plugged it back into the equation that I labeled star, and then you ended up with what was u2, which was 1 minus I over h bar integral ti until t of Vi t prime t prime plus terms of order 1 over h bar squared, right? So in the end, what we managed to do was that we were able to find what this operator was, and that was the operator that we needed in order for us to compute our transition probability. So if I summarize, so you get that U as T Ti. This we solved by I think it was Tuesday. You find that you get it as a series Vi of T dt prime plus minus I over h bar integral Vi of T1 dt1 integral V2 V of T2 interaction picture dt2 plus dot dot, and then you inserted this into your equation for PIF. So the probability transition from I to F is just psi I or the mod, and then you insert this evolution operator Ti psi F squared, and then you just make use of this sense that you got. So once it hits that one there, you get psi F psi initial minus I over h bar psi Vi psi final Vi psi initial, right? Remember that this again is still in the interaction picture, and then the only thing that will be left then will be dt. And then because we wanted to find the transition probability, that you started with some state psi initial, what was the probability that it will go into a different state, which will be psi f, then this term was not there, and then we were done because now we were able to find what the transition probability was, which I think I did in the previous slide. So the final expression or the final result of what we were doing on Monday was this equation here, right? And the only thing that I probably didn't go into detail, which I just naively thought would be easy, was how to get in that exponential of the angular frequency. And that arises because if you saw, we were working in the interaction picture. So you write out what the interaction potential would be in terms of the potential. It's being evolved by the unperturbed Hamiltonian. And because we are working with unperturbed Hamiltonian, so you know precisely what happens when okay, let me start here. You know precisely what will happen when e to the I h0 is there, because these are eigenstates of h0. So you get that e to the I h0. For now, I'll set h bar to be 1, t acting on psi I, because they are eigenstates of psi I. This just gives you e to the I, e initial, t, v, and similarly, once this operator or exponential of that operator is there, this gives you e to the minus I, e final, t. Okay, if you want, you can put those bars there. But the point was that these are C numbers. They are no longer operators because you have acted on them. They just give you the energy e to the exponent of the energy. That's a complex number, so you can play around with them. So in other words, you can remove them from the expectation value. So this is in the Schrodinger picture, psi I, and then left with e to the it, right? E final minus e initial, and then over h bar. And this thing here is what you usually call the angular frequency. So that summarizes what we did on Monday. The point was that you ended up with this expression. So for today, we will look at various examples for that v of t. So we will look at it when it's a constant. So you just between time 0 and tau, you just switch on your perturbation, and then after some time you switch it off, and then you will try to calculate what this transition rate will be. The other one would be once it's sinusoidal, so it's either going to be sine omega t or cos omega t. And then just to give you a feel of these different pictures, I gave you an example, or I gave it as an exercise. So it was calculate the position and momentum operator in the Heisenberg picture. And once you have that, then go ahead and try to compute the Heisenberg equations of motion. So as a feel of how you go about doing this, I did that exercise. So if you remember, the Hamiltonian for the harmonic oscillator is p squared over 2m plus half m omega squared x squared, right? Remember that for this type of things, what you need is that you need e to the I h over t h bar t acting on the operator e to the minus I h t. You have to, in the second expression for omega only 10, I don't understand the fraction 1 over 3. And let me just read that. So there was a question in the second expression, page 10. Don't understand why the fraction has a coefficient 3. Which page? Which example are you referring to, which has a 1 over 3? Because not okay. Current page. This page, or there's no 1 over 3. Don't understand why the fraction so coefficient of 1 over 3. Trying to think. Just example, page 9. You are referring to this page that's on the screen. Oh, okay, I see what you meant. So if you look at what I just explained, so this, you have to calculate what is omega. Now these angular frequencies, these are just given by 1 over h bar of E final minus E initial. And given that for this particular example, I think we were working with the infinite potential well, and we know that for the infinite potential well, n is given by n squared pi squared h bar squared over 2m a squared. So E n final, so E n final minus E n initial, this will give you, you can factor out pi squared, they're the same h bar squared over 2m a squared. and the energy just depends on the squares. So I was moving from, I wanted to calculate the probability that I go from the ground state to the first excited state. And for the infinite potential, well, you don't start at n equals to 0, you start at n equals to 1. So the ground state is n equals to 1. And then the excited state was, the first excited state corresponds to n equals to 2. So the final state will have n equals to 2, which is 2 squared minus, and then the ground state was 1. So this 4 squared minus 1 then gives you the 3, which is this 3. Okay. Right. Okay, so let's return to this example, right? So what is the position and angular momentum in the Heisenberg picture? You know that in the Heisenberg picture, any operator in the Heisenberg picture is just given by e to the I h t over h bar. Operator in the Schrodinger representation, e to the I minus I h t over h bar. Unfortunately, these are operators, so they don't really commute, but there is a mathematical identity called the Barker-Hausdorff identity. So this states that if you have, say, an operator E and it's acting on EA acting on B, e to the minus A, right? That this is given by B plus the commutator of A and B. Right? Let me just say this is called the Baker-Hausdorff identity. So then then you iterate. So this will give you half commutator of A, B plus 1/3 commutator A, B, all types of commutator. So you're just going to make use of this mathematical identity. Right? But as you can see, you have to first find what these commutators are. So I went and computed the commutator. So just given the so you make use of this identity. And I had already computed what was h comma x and what was h comma p. So if you just plug everything there, you ended up with x. So the operator x in the Heisenberg representation will be given there. And this you had already computed in the previous page. So that gave you p, x, p. But once you start grouping your terms, then you can recognize that this is just cos omega, and then the other one will be sine. Similarly, if you do it for cos, and then the equations of motions, you can show that they're given by that. So because my point is that for this chapter, the important thing that you should be able to compute is that if I give you any time-dependent perturbation, you should be able to compute the probability that it makes a transition from one state to the other. So in the next example, I gave you a hydrogen atom with some electric field, which is time-dependent, and I'm asking you for the probability that you go from the 1s state into the 2p state. So we just use that formula that we derived. Okay. On Tuesday, so P1s going to 2p, this will be given by 1 over h bar squared, integral minus infinity to infinity, 210, acting on v as a function of t, 100, and then you still have to multiply this thing inside the integral by I omega final initial multiplied by t prime. Let's call that t prime dt prime, right? And then you square that. So the first thing that you have to do for this computation of these transition probabilities is that you first have to find what is psi final v as a function of t, and then psi initial. This is the first thing that you have to compute. So if this was time independent perturbation theory, then you will be done. You just calculate psi n, v psi n, and you're done. But for the time dependent one, you still have to do the integral over the time weighed over by this exponential of the angular frequencies. So let's go ahead and try to compute what is psi f v of t psi I. So that gives you 210. V of t is just given by e. You can take the e out, multiplied by that, tau squared plus t squared. This doesn't depend on the axis because so you will be left only with the z100, and then you write what your wave functions are. So psi s1s is just the ground state, so this gives you e to the minus r over a over square root pi a cubed. Then psi 2p is given by the radial wave function r1 y0. If you put everything there, you get 8 pi a cubed r over 2a e to the minus r over 2a and cos theta. Right, so you just plug this into your expressions, and you then find that 210 z100, this gives you 0 to infinity. So once you start multiplying everything out, you still have to do the integrals over the radial coordinates r3, r21, r10, dr. Then you still have to do the integral over the angle. So this just gives you d theta sine theta cos squared theta. Integral over d phi. Nothing in these things will really be depending on phi, so you just get 2 d phi. This gives you a effect of 2 pi. Once you do the angular, and also the angular, the integral over d theta is also simple. I think everyone can do that integral. So the only integral that will be left will be the one over the radial coordinates. So you get 4 pi over 3, 1 over 4 pi 4 square root 2. So during the test and exam, I will always ask you this type of questions. So you should be able to do what I am doing. Get 0 to infinity, r to the 4 e to the minus 3r over 2a dr. So this is the only integral that's left, and this is a gamma function. Right? If you remember, gamma of z is given by e to the minus t z minus 1. So if you change coordinates, call that thing t there. So and play around with that. So in the end, you end up with that your integral is just going to be, to simplify, to 2 to the 8 multiplied by a0, 3 to the 5 square root 5. So you end up with that the probability of transition from 1s state to the 2p state will be given by 2 to the 15 e squared e0 squared tau squared a squared over 3 to the 10, but we are not yet done because remember that everything here was inside a integral over the time, so we still have to do the integral of I t or final I over tau squared plus t squared from minus infinity to infinity of dt. Does anyone have an idea as to how you go about doing that integral? So we are nearly done. We just are left with an integral over the time. Any suggestions as to how to do the integral? So if this example came up on the test next week, how are you going to do that integral? Maybe you have seen the residue theorem, right? Good. Then you just apply the residue theorem. So let me just quickly do that. So the integral minus infinity dt over if you want, you can call them Z, but what I'm saying is that you can say dt is a complex thing, analytically continue to the complex plane and call it dz, but doesn't matter. So you can write this as plus I tau, tau minus I tau, it. So it will have a residue, maybe let's say that at say as the other way around, but it doesn't matter. But this will give you 2 pi I multiplied by the residue, and the residue will be given by the limit as t goes to I tau, the other way around. So this is t plus I tau. Right? Limit as t goes to I tau of t minus I tau. I think everyone has seen this, so I'll just be quick. T minus I tau, t plus I tau. So that cancels that, but there's still this integral over the angular frequencies. So you get e to the I omega final initial t. Everything cancels, and then you're just left with 1 over 2 I tau e to the I omega final initial, and the time is just replaced by I tau. So this gives you e to the minus tau over, and then there's 2 pi I. So 2 pi I, the 2's cancels, i's cancel, so you're just left with e to the tau over tau over tau. This is the final result, and you just plug it into your thing. So then the only thing that you will still have to compute will be this. So if you recall omega, there are too many steps in these types of calculations, but omega final, this will give you, so for the one, for 2p, this gives you 1 over 4 of the Rydberg number, which is the 13.6 electron volt, and then in the 1s, this gives you that. So this gives you 3 over 4 of the Rydberg. So once you put everything into the expressions, you end up with there. So this is the transition probability that you go from the 1s state to the 2s state once you put that perturbation where v of t was given by 1 over t squared plus tau squared. So I will give you various example, various things, but for today we are only going to focus on the case where v of t is a constant, and also v of t is just a sinusoidal function, so it might be e to the I omega t plus v dagger e to the minus I omega t. These are the two cases that we will be considering next. Right. So let's start with the case where v is a constant. Let's see. So let's go back and write the equation. So you know that P I F is going to be given by 1 over h bar. But because now your v is a constant, you can take it out of the integral over the time. So you just get psi I v psi final, and then you take the mod. But now you will be left with an integral over 0, and this will answer, because on Tuesday there was this question, if I take the mod squared of that, will this always cancel and you just get a constant? But now you will see that the mod, or the absolute value, which is called also the modulus, now it will be a function of time, and you will see how that comes about. So let's say you're integrating from 0 to t. I'm saying that I'm looking for the case where you have constant perturbation. So you have to do an integral over dt. But if it's a constant perturbation, you can take it out of the integral over time. So you will be left with e to the I omega final initial t squared. And everyone can do this integral. You just get 1 over omega final with that I. And then you get, but we still have to square. So you get I omega final initial multiplied by t. Remember, this is a dummy variable, so that's t prime. Then we're evaluating this between 0 and t prime, so you get that subtract E0, which is just 1, right? And you have to take the mod of that. So the mod in the bottom, you get omega final squared, and in the numerator, you get omega final initial t minus 1 e minus I omega final initial t minus 1. So you get 1 over omega final I squared, right? If you multiply those ones, you get 1. Then if you multiply the exponentials, you also get 1. So this gives you 2 minus, and then you get the ei omega t minus e minus I omega t. Right? And this is a trig function. So if you just apply the Euler formula, you get, so 2, this is what we got from the previous slide. If I write ai omega t minus e minus I omega t. So what is this as a trig function? I think in one of the exercises, like yes, but it's a trig function. I gave you, okay, let me just do this properly. So you are all happy with the Euler formula. So if you look into the minus I phi, will give you cos phi minus I sine phi. So let's say this is equation 1, this is equation 2. So if you add 1 plus 2, you get ei phi plus e to the minus I phi. This will give you the that. So if you're just adding them, these terms will cancel. So you get 2 cos phi. So this means that the expression that I had there will simplify into 2 cos t to 1 minus cos omega t, and this is 2 of sine squared omega t over 2. And then so the thing that we wanted was, we wanted to take the mod. So this means that the mod of that will give you 4 sine squared omega t over 2. But so how do you get the sine squared when the cos is not squared? Okay. So if you go back to high school, I think you had this cos 2, let me call it cos 2 theta was given by 2 cos squared theta minus 1, which was 2, which was 1 minus sine squared theta. So if you just look at this one, right, with a 2 there, so this gives you cos 2 theta. So this means that you can solve for what is sine squared theta. So sine squared theta is given by 1 minus cos 2 theta over 2. So this means that sine squared theta over 2, and my theta is just omega t. So this gives you, whenever I saw the 1 minus cos omega t, then I can replace it by, yeah, something like that. So the point was that in the end, you express everything in terms of sine. Right? There. Let me see. I didn't realize it was cos 2. It's not that it's cos, it's cos theta, and then you can rewrite this in terms of sine squared theta over 2, which is sitting there. Right. Okay. Right. And this is the final result that we have. So when v is a constant, you can take it out, and then you're left with integral e to the minus omega final it dt from 0 to t. Once you do those integral and you take the mod, you just get sine squared omega final t final over omega final squared in the denominator. However, there are various representations of the Dirac delta function, and one of them is given by limit t going to infinity of sine squared y over pi y squared t. This gives you Dirac delta function of y, right? In terms of a Dirac delta function. But before that, you can try to plot this function. And then in the limit as t goes to infinity, you make use of this identity and write everything in terms of a Dirac delta function. So in the limit as t goes to infinity, this is what you get. And then you might also be interested in the probability per unit time, so which is the quantity called transition rate. So that is per unit time, so you have to divide the PIT by the time. So once you do that, you get 2 pi over 8 bar psi final v psi initial squared, and then you're left with the Dirac delta. I think yeah, you just divide that t there, so it goes away. So once you divide by the t, this is what I'm calling the transition rate. You can also have a state where, so what we have been considering so far is that you start with some initial state, and all these states were discrete, and you wanted to check what was the probability that it goes to a final state, which was one of these discrete states. But it might happen that your system, what usually happens is that it has a continuum of states after some state. Maybe when, let's say, you're labeling them by n, and this n is very large, then you end up maybe with a continuum state. What is the probability that if you started with one of these states, that it actually ends up in one of those continuous states? So for continuous states, then first, I think you might have seen this statistical mechanics. You define the density, which would be the number of states between E plus EF plus delta EF. Define it in this manner. So this means that your number of particles in that energy region will be given by just rho EF, DEF. Then you try to integrate out. But because there is this Dirac delta function, once you try to integrate, so I'm saying that you have to multiply this maybe by delta n, which is rho of E, F, D, E, F. And then you have to sum, so you have to integrate out all these states. But because of this Dirac delta function, this only evaluates to E initial. So in case that you do that, you end up with this, and this is also called the Fermi rule, because it's just saying that if you started with a constant potential, then after some time, as t goes to infinity and make use of this approximation to the Dirac delta function, then your transition rate then become constant in time, so they become time independent. So then the other case that we will then be looking at will be what happens when you have a harmonic perturbation. So that's what we want to do. Next slide. Okay. Are there any questions so far? So the next case that we will be looking at will be if you have v of t. So it's either it's expressed in terms of sine omega t or cos omega t, but because we have to do integrals where the integral is already of the form I omega t, it's best to write everything in terms of the exponential. So I'm saying that now we are considering time-dependent potentials of the form v e I omega t plus v dagger e to the minus I omega t. Then we plug this into the expression PIF. This will give you 1 over h bar squared. Right. So it splits into a sum. So you get psi final, and this v are constant. So you get v psi initial, but you still have to do the integral over the time. So you get 0 dt prime, 0 t e to the I omega final. But there's also this omega there. What's the question? So you end up with omega final initial minus omega multiplied by t. Then you do it for the other part. So you get v f v psi initial integral from 0 to t dt prime e to the I omega final I, but now it's coming with a different sign, and this is dagger plus omega multiplied by t, and then you have to square everything. Now, when you square, remember that this v, it's a perturbation, so if you want to write everything out properly, it's lambda multiplied, well, lambda is a very small number multiplied by v. Similarly, lambda multiplied by v dagger. So the cross terms, which will be the terms, so what I'm saying is that once you write everything out, you get 1 over h bar squared, psi final v, psi initial, mod squared. So you get the square of that term. So this will give you integral 0 t dt prime e I omega final initial minus omega t, right, squared. You also get the same term, but now with v, the square of the other term with v replaced by v dagger. But it will be these cross terms which you get by multiplying these terms, and those terms you can ignore because they will be of order lambda squared, because this is lambda v, that's also lambda v prime, so they will come with a term, they will be subleading, so you only have to consider the square of those two terms. So you will again be left with having to do the integral from 0 to t of dt prime. Now you have e to the I omega final initial plus omega t. And you have to the mod of thing. And because you will be doing this over and over, so let me just redo it again. These integrals over these dt's. So how you do that, if I give you something that's only depending on the exponential and you're left with an exponential, that integral then will give you omega final plus omega, plus or minus, right? Because you have two terms, one of them they differ by a sign, so plus or minus squared. Then you still have to, once you integrate that, you get I omega final integral plus or minus omega t minus 1, the mod of that squared. So this gives you 1 over omega final initial plus or minus omega squared e omega final initial plus or minus omega t minus 1. So you multiply that by the complex conjugate, I omega final I plus or minus omega t minus 1. So for now, I will be ignoring the term in the denominator. So we are only left with that. So once you multiply everything out, this multiplied by that gives you 1. Similarly, that multiplied by the minus 1 multiplied by the minus also another 1 minus 2e what will I get? So if you multiply that with that minus 1, you get e to the I omega final I plus or minus omega t minus e minus I omega final I plus or minus omega t. And this you rewrite this as in terms of a trig function. So we've done this before. So you end up with 2 minus 2 cos omega final initial plus or minus omega t. Right. Repeat what I did previously, so you end up with omega final initial plus omega t. And as I said, 1 minus 2 sine squared theta over 2, this will give you cos 2 theta. So 1 minus cos of maybe cos theta. So 1 minus cos theta is given by 2. So this gives you 2, something like sine squared theta over 2, which is omega final initial plus or minus omega over 2 multiplied by there's a 2 there, so this gives you 4 multiplied by t. So this is the result of having to do the integral 0 to t of dt prime of e to the I something. And then but there will be 2 sums, so and then you repeat the same thing, that sine omega limit as t goes to infinity, sine omega over omega squared, that this gives you some Dirac delta function. So then you end up with a Dirac delta function there and another Dirac delta function. So the only time that this is non-zero is only if EF is given by EI, plus or minus. But let me just separate the cases. So you get that E final is given by EI minus omega, or the other way around. And if you look at the diagram when this is non-zero, so let's say that the case where, so you start with EI and you ended up with, so this will be continuous, you have absorbed some radiation of, or some photon with energy h bar omega, and then you ended up with final state, which is given by the initial plus h bar omega. Or you could have started with E initial and then you emit a photon, and then you transist into a lower state. So EF in this case will be given by EI minus the h bar omega. So you're dealing with either stimulated emission or just plain absorption, which are these 2 cases there. Are there any questions so far? Okay. If there are no questions, then the next thing that we will be looking at will be adiabatic and maybe sudden approximations. So far what we have been looking at was the case where we just assumed that our v of t was small, so was less than 1. But it might happen that we turn on this potential very, very slowly. So it happens So you start with some state psi n. Then if you're doing this very slowly, say this is psi n of 0, you change by doing this adiabatic. You are going to change this from h of 0 into h of t. But if you're doing this very slowly, what will then tend to happen will be that you end up with a same system. So naively, you will think that psi n of t, that the state doesn't really change. So if the potential dv over dt is changing very slowly, then PIF, you expect that PIF, if you started with something and then you just apply a sudden change in the Hamiltonian, again in these two things you expect that this to be zeros, but we have to check this by using our formula. So for the adiabatic change, you have to consider dv over dt. Unfortunately, if you look at the thing that we are squaring, there is no dv over dt. So to do that, you first have to rewrite that. So if you take d over dt, ei omega, maybe let me just write everything on a clean whiteboard, because that's going to be missing. Okay. So I was saying that we have to introduce terms like dv over dt, but there was no time derivative. So I'm saying that it's best if you go and you write omega final I multiplied by t. Now, if you were to take this as derivative, so this will give you 1 over I omega final initial of e to the I omega final initial t. So you are going to use this to introduce a time derivative into your expression, right? So this is what I was saying. Let me just go back. This. Right. So wherever there was that exponential term, you replace it by 1 over omega d over dt. So replace that there. Right, now we are there, and then you integrate by parts. So you can call this to be u, then your du will be derivative with respect to time of this term, which gave you that. And then your v will just be the integral. So v will be integral dt prime d over dt prime ei, which is just the exponential. So you get that. That's the exponential. But our perturbation was that it's switched on at time equals to 0 and also switched off at some later time, which is t. So once you evaluate, I'm saying that v of 0 is the same as v of t. So this term drops out, and you will only be left with that term then. Right. And we do the same thing. I think by now everyone is happy that the integral 0 to infinity, or the mod of this ei omega t squared, this just gives you sine squared omega final initial t over 2, which is that term there. And then you still have the square there. And because dv over dt is varying very slowly, right, with respect to the energy. So for the adiabatic case is that this is very small. Sine squared is also smaller than 1. So this again is way smaller than 1, which is what we expected, that if this will be going to 0, because the probability of that, if you're changing your system very slowly, psi n will slow evolve into psi n of some t. So the probability that it goes maybe from psi ground state into psi 1, these types of probabilities will be negligible or nearly zero. Right. And the other case that we will have to look at will be is an approximation. So for certain approximation, you have this Schrodinger equation, which you can solve, but say you just say you started with some state psi m, which can be expressed in terms of this basis, then you know that in this case, then the probability in going from m to n is given by the square of these things. So it's just c m squared, which is just the overlap psi m psi m. So for a certain change, you can just go ahead and use of the formulas that we derived in, I think it was chapter 2 and chapter 3. But if you look at the expansion, the thing that will be varying very slowly will be the e to the I omega t, which you can take out. This gives you a sine squared. And then by fundamental theorem of calculus, this just gives you that. So I'm saying that that just simplifies into psi f v of t prime psi initial, and then you square that. So instead an approximation, the probability it simplifies to that expression. So let's then consider this example. So you have a particle which is initially in the ground state of an infinite potential well, right? And the walls are at 0 and A. So there are two cases that you could consider. So you move these walls very, very, very slowly until you end with them at 8A. And then the wall is moved slowly to x equals to 8A, and the energy of the wave function of the particle in the new way, calculate the work done. So the work done will just be, so you know that the energy En is given by h bar squared pi squared over 8 m squared. This is when the wall is at x equals to a. Once you move this very slowly to the new wall, so then your energy En prime will be given by h bar squared m squared pi squared over no, this is 2, right? We started with, initially it was 2 ma, so 2 m, right? And now you move it to 8a, so this gives you 8 squared. And then the energy will be energy difference, so this will be En minus, let's see, En minus En prime. Let me see what it is. So I get, okay. So I was saying that the work done, the work should be negative, I think. Let me just check. So I get E will be given by E1 at a later time minus E1. So I'm just saying that this is E final minus E initial, and E final would be I squared H bar squared over 8A squared M minus pi squared h bar squared over 2ma squared. I'm not getting a negative number. I got 63 pi squared h bar squared over 128 ma squared. The wall is moved. The work should be negative. I just computed, so I just took the final expression for, so E final is just given by 1 over, it's going like 1 over 8a squared. So this gave me over 128, it's a 2 ma squared. Right? So this gives me pi squared h bar squared over 128 ma squared. Then I subtract 1 over 2ma squared pi squared h bar squared. Let's say I multiply this by, yes, to me it looks correct, just a positive number. But I'll check, because I think when I did it I got plus 63. I don't see negative. And then if it was done suddenly, so if it's done suddenly, then the probability is you just use the standard versions that we have from chapter, I think it's chapter 2 and chapter 3. So then the probability is just the overlap of psi 1 for the new Hamiltonian in when the wall is at 8a, then you take that with psi 1 of the old one, and then you have to square this. So you just have to compute what these overlaps are. So let's try psi 1 prime, psi 1. This gives you 2. Let me just write everything out. So this is 0 to a, psi 1 of x, psi of x. This gives you 2 over square root 8a, integral from 0 to a sine pi x over a, sine pi x over a. So they are, all of them are in the ground state. The only difference is that the wall for the other one, what we call the wall for one of them is 8a. So if you compute those integrals, you get 16 over 63 square root 4 minus 2 square root. And then the probability then would be the square of that. So the probability 1, this gives you the square. So it's just the square of 16 over 63 pi square root 4 minus 2 square root 2 squared. Then the first excited and so you still have to compute things like psi 2, psi 1. So this gives you 2 over square root 8a, integral from 0 to a of sine pi x over a, with 4 now, because the wave function is sine n pi x over a, and the first excited state then will correspond to n equals to 2. So you get 2 divided by the 8, which gives you that 4 over 8, then sine pi x over a. And, I think people should be able to do these types of integrals, so you get something like 8 over 15 pi. So then the probability that it transitions to the P21 from that, this will just give you 8 over 15 pi squared, which would be 17%. Okay, I think I'll stop the recording here. Then you can ask any questions.